Hello everyone. My name is Li Ding, and I'm a PhD student at UMass Amherst. Today, I would like to talk about our work on evolving neural selection with adaptive regularization. So let's start off with the ordinary neural network. So as we all know, for modern deep neural networks, we have millions of neurons and connections, but usually we are only classifying a few classes comparing to the network size. So over-parameterization is one of the inherent characteristic which may cause overfitting problem. So overfitting is just you are memorizing all the training cases within your neural network with all those parameters. So we have some good prior work to overcome this issue. So one of these is the dropout method. So for dropout, the neurons and connections are dropped at a random ratio for all the input during training, so that for each training batch, you are actually selecting different neurons so that it's very hard for the network to memorize the training cases. So our intuition for this work is the human working memory. So as we know, the complex tasks often require that human working memory to be flexibly and independently maintained, prioritized, and updated according to the changing task demands. And similarly, in computation models, inadequate computation resource may cause undermine model performance because the model is just too simple to handle the cases. And on the other hand, overwhelming resources are likely to make the model overfit by just, for example, memorizing all the training cases. So here we propose this adaptive neural selection ANS framework for deep neural networks. So the neurons are adaptively weighted and the weights are predicted by a self-attention module regarding the input. And we would like the model to have the behavior of such that for easier cases, more neurons are dropped to prevent overfitting. And for hard cases, more neurons are selected to handle those cases. So the ANS framework consists of two parts. The first part is an attention module. So the attention mechanism attempts to implement the action of selectively concentrating on a few neurons in the deep neural network. And this has been proved to be useful for many tasks such as natural language processing and some just neural and used in many neural network architectures. And here is a basic definition. So we use Z of L to denote an attention layer with another pair of weight matrix and bias vector, because it's just as similar as a linear layer. And the forward pass operation of a neural network with attention module is described as the following. And for another part in the ANS framework is we call adaptive regularization. So for layer L in the neural network, we use G of Z of L to denote the self-attention unit, where we see G is the activation function of the Z of L is the attention weight. And the regularization is calculated as by this function where we have this gamma is a variable that controls the extent of the regularization, which I will describe in later slides. And we have this K is the number of all neurons as a normalization factor. And this L1 norm is simply, we're just counting how much attention are used in this layer. So basically indicating how many neurons are selected in this layer. And let's suppose the chance of overfitting is higher when the model performance is good. We need greater regularization to guide the network to use fewer neurons to form more generalizable representations. And to achieve this, we calculate gamma, which is the regularization factor, as alpha times m to the power of beta. So here, alpha and beta are hyperparameters to control the scale and variant of gamma, and m denotes a non-negative metric of model performance on the current input samples. So for example, if we are doing for the image classification task, m can be just the accuracy, like the batch accuracy of the current training batch. And we can see that if m is high, like 1, you get 100% accurate, then you have a larger gamma because it is likely that the model overfits and you're just memorizing all the training cases. So you need to drop more neurons so to force the model to learn some more useful representations. And then we need to actually make it work. So we're trying to evolve this adaptive neural selection behavior. So inspired by the parent selection methods in GP, ANS introduced a selection pressure to the current neural network by injecting regularization on the number of neurons currently being used for the input training sample. So that means by putting attention weights on the set of neurons for each training sample, the selection process is actually evolving different subnetworks and subnetwork variants adaptively according to the input sample. And such evolution improves as the training proceeds because the evolution doesn't interfere with the network training itself. Finally, all the subnetworks will have the capability to correctly classify the current input sample. And here's an illustration of our method. So we have this original model, which serves as the parent, and plus we have this attention weights. The attention weights based on the input choose different model variants, which are the children's for each regarding each input case. And we have this adaptive regularization to evolve the attention weights so that it evolves the behavior of selecting more neurons for hard cases and less neurons for easy cases. And here is the algorithm. We can see that this algorithm is pretty similar to the classic training, deep neural network training process, but we are just adding this evolution with adaptive regularization inside this training loop so that we are not adding too much extra computation in the training loop of the deep neural networks. And now for experiments, we implement and test the proposed ANS framework to common confident architectures for supervised image classification tasks. And we use CIFAR10 and CIFAR100 datasets, which are the common benchmarks. And here are the results. So our ANS method significantly improved the model performance, especially on harder benchmark CIFAR100, because, and we can see the numbers here, because CIFAR10 is just for 10 different classes, so it's a much easier benchmark than a CIFAR100, and we can observe better improvement on CIFAR100. And we also perform ablation study on training. So we see that our method, which is the red solid line, has better, faster training convergence comparing to other, the vanilla model and model with Dropout. So that means our method actually improves the training convergence because it is evolving this behavior of selecting different amount of neurons for different training cases, which actually helps with the training process. And we also perform ablation study on the model variants. So the ANS framework consists of two components, the self-attention module and the adaptive regularization loss. We want to see what are the contributions of those two parts. And here are the results. So we can observe that with the self-attention module only, ANS is already able to improve the performance because the self-attention module is helping the network to have this concentrate effect. But by adding the adaptive regularization, the performance is further improved to a larger extent. So actually the adaptive regularization is more important for evolving this behavior of selecting different amount of neurons for different inputs. And here we also did a study on the fitness function of neuron selection. So we have this, the neuron selection, we have this gamma. We know this gamma is controlled by two hyperparameters, which according to the metric. So ANS, we find that ANS is relatively robust to different hyperparameter settings. As we can see here, most of the ANS hyperparameter settings outperforms the baseline method. And finally, in conclusion, we propose the adaptive neural selection ANS framework for deep neural networks to evolve the behavior of selecting specific neurons to perform the task. ANS can significantly improve model performance on generalization capability to unseen test cases without slowing down the training process. And also for future work, we can see that ANS can also be optimized by using non-gradient neural evolution techniques because it doesn't rely on gradient computing. And it can also be used to evolve network architectures, serving as a strategy for neural architecture search, which is a hot topic for current research. So for example, instead of using attention like this work, we can have other terminologies to control the complexity of deep neural networks, such as we can control the number of layers, the number of neurons used in the network, and those can be evolved by using this ANS framework. So thanks for listening, and I'm happy to take questions.